Hi everyone, I am Nimisha. I'm going to be your TA for the session, for the TA sessions, live TA sessions for NPTEL course Introduction to CFD. So today we'll be looking at the week 0 assignment, which you can see on the screens. And the other TA must have taken the first 7 questions, the first 8 questions of this assignment, and I'll be taking the next 7. So let's get started. The first question concerns with a normal shock wave. So over here there's a mention of the supersonic wind tunnel. You don't have to worry about where that shock wave is much. You just need to know that there is a shock wave. So then over here, let's draw a shock wave. We have our normal shock wave. Now on the left hand side, let's see that is upstream of the shock wave. Let's see what all is given to us. Over here we have the Mach number, we have the pressure, we have the density. So M1 is 3.5, P1 is 1 atmosphere, and rho 1 is 1.2 kg per meter cube. That is the density. So we are asked over here to find the pressure and density downstream of the wave. That is, we need to know the P2 and the rho 2. This is the question. So over here, let's see what we already have. We have the Mach number. For a normal shock wave, that is enough for us to know the downstream properties. So what we'll do is that we'll look into our gas tables and we will try to find where this M1 is on our gas tables. So we'll just try to find M1 on gas tables. So corresponding to M1, we have P2 by P1, that is the downstream pressure by the upstream pressure, equal to 14.12, and we have rho 2 by rho 1 is equal to 4.261. Okay, so now let's see what all we already have. We have P1 from the question, we have rho 1 from the question. So in order to find P2 and P1, we will just be multiplying the P1 to the ratio of P2 by P1, and similarly for rho 2 we will be multiplying rho 1 into the ratio for rho 2 by rho 1. Okay, so this gives us 14.12 bar and 5.11 kg per meter cube. Okay, so that solves our first question. Then moving on to the next one. So here we are required to find the integral for x into ln x. So this is a problem that requires us to employ integration by parts, which is a fairly common method we must have all used in class 12. So let's have a look. So first of all, we need to use integration by parts. So the formula for that is that you integrate uv dx, where u and v are functions of x, and here's what you get. Fairly common formula, we have all been exposed to it earlier. But the crux of the matter is to choose the correct u and v over here. So let's see how to choose that. What is important over here to note is that one of our functions undergoes integration while the other majorly goes through differentiation. That is, u is the one that needs we need to have a derivative of u. Meanwhile, we need to have an integration of the v. So we'll choose our function smartly, and over here in this current problem, we will choose our u to be ln x, because we do not want to perform integration over log x, because integration of log x is another complicated thing to do. Meanwhile, we'll choose the x to be v, which is fairly easy to integrate. Okay, so moving on, let's see what that gives us. So we have over here ln x into integration of x dx minus 1 by x, the derivative of log x is 1 by x, into again integration of x dx. Okay, So we have ln x into x square by 2, okay, plus c, let's not forget the constant of integration, and into x square by 2 plus c. Right. So fairly simple question. We're able to get the answer quickly. Okay. Okay, next we have an interesting question. This talks about the boundary layer approximation of Navier-Stokes equations. So the boundary layer approximation on its own is a little bit of a long topic as such. Basically, in order to get a simplified version of Navier-Stokes equation at the boundary layer, that is, what is the boundary layer? Like for example, if you have an airfoil over here, then there is a region of there's a region near the wall. This area is called boundary layer. So basically, what this boundary layer is that it is a area of very high gradients. So you know that for at the wall we need the no slip condition to be active for velocities u, v, and w, and so that's a very drastic change from the free stream velocity, because at the free stream that is outside of this boundary layer, the velocity is going to be something of the order of whatever it might be, u infinity, which is going to be high. So then from going from u infinity directly to zero, it's like a big jump. So then there is a this area of high gradients is known as the boundary layer. So basically, the answer to this question, just in case we just need to know the answer, is that the equations are parabolic. Now, why they are parabolic is that by using approximations based on the dimensions at the boundary layer, we get a modified Navier-Stokes equations near the boundary layer. So let me know later on if you want me to go into detail regarding this. Um, but for now, I will just give you the equation and show you why it is parabolic. Okay, so because of the reasons that I just mentioned, that near the boundary layer, by using some typical magnitudes of u, v, the length, the width of the boundary layer, etc., we get a modified form of the Navier-Stokes equations at the boundary. So that looks like u du by dx plus v du by dy equals to minus 1 by rho dy. This is for the x momentum equation, x momentum, so that we don't get confused. Okay, plus by dy square. So you see that this basically, this is your normal advection terms. Okay, this is only in two dimensions, so do not get confused as to where y is. And over here we have the pressure term. Then this is the viscous term. This is the mu is the kinematic viscosity. Okay. So we see over here that we have the advection terms, we have the pressure term, and we have only the viscous term in the y direction, because the viscous term in the x direction is very small. Again, because the gradients in the x direction in this sort of situation are going to be very small as compared to the gradients in the y direction, because that is a very drastic drop. So compared to the viscous terms in the in the y direction, the viscous terms in the x direction are effectively negligible. That is the idea behind this equation. So over here now they've asked us to mathematically categorize this equation into what it should be. So then for categorizing a PDE, PDE, we have like a standard form of partial differential equations. I'm just going to take 5 for any odd function in x and y. That is, so we have a equation of the form this kind of a form. This is just a generic equation. So then this, whatever this partial differential equation is, that has a the right hand side of this is going to be a function in x, y, the phi and the gradient of phi in the x and y. This is again a two-dimensional representation. Do not worry about the z direction for now. And so then we have some what rules to categorize them. That is b square minus ac in this sort of a form. If that's equal to 0, it's a parabolic equation. If b square minus ac is greater than 0, it's a hyperbolic equation. And if b square minus ac is less than 0, then it's an elliptic equation. So let's see what our b, a, etc. is in our current problem. So, okay. So b over here, we don't have a b is equal to 0 for us. We don't have an a. So a is also equal to 0 for us, and c is equal to the new. Okay. Here the function phi is u. So we see over here that if we do b square minus, if we go with b square minus ac, what we're basically getting is 0 square minus nu into 0. That is equal to 0. Therefore, our equation is parabolic. Okay. Next, we have a question regarding the pressure drop for a laminar flow through a pipe of diameter d, and we're asked what is it proportional to, with like what is the relation with velocity of the pressure drop. So this is a fairly commonly known formula for delta P. Delta P is equal to the friction coefficient into L by D into rho by 2 into the flow velocity. So over here the flow velocity is Vf square. So clearly we are able to see that the proportionality is with Vf square. So we have the answer for that. Okay. Next we have the we are asked what is the expansion of a what is the expansion of e raised by minus x by 2 as a polynomial of degree 3. So first we look at the normal expansion of e raised to the power x, for instance. So e raised to the power x has a standard expansion that looks like 1 by x by 1, x square by 2 factorial, x cube by 3 factorial, so on and so forth. So we are only concerned with a polynomial of degree 3. So I'm not going to be writing further terms. But over here we see that this is just for any odd e raised by x. So substituting x minus 2 instead of the x over here, let's see what we get. 1 plus. So obviously we don't have to disturb the coefficients as such, because those are not involved in our computation. Like, we don't have to change it because we've done nothing to warrant that change. Right. Then 1 minus x by 2. Okay. Then we have here x square by, what is 2 square? 4 into 2 factorial. Plus we have, or rather minus x cube by 8 into 3 factorial, so on and so forth. So that gives us 1 minus x by 2 plus x square by 8 over here minus x cube by 8 into 6, that is 48. Okay. So this is a solution along with the higher order terms. We will not get that. So this is the solution. Okay. So moving on to the 14th question, we are simply asked a definition of a stream tube. So what is a stream tube? So basically, stream tube is just sort of an imaginary tube, a path, or rather, a tube is a good enough word. So it's a tube that is made out of streamlines and which can be visualized as a path for the fluid inside to flow through. So this is just like a visual tool which is made of streamlines. So let's see what matches our definition of the stream tube in from all of these options. So once again, just to visualize that, I'm going to be drawing these streamlines. So I have streamlines over here, and just these dotted ones are on the other side of the fluid. So this sort of a, let's pick another color. So over here we have like a tube kind of a situation, which is like comprised of all of these streamlines behind as well. So then this is my stream tube. Okay, so stream tube is a tube to transfer fluid from different sinks and a source. That doesn't sound very close to what I want. Is a tube to extract the fluid from, no, from separate sources to transfer to a single sink? No. Is a surface in a flow field formed by streamlines, because it's a visual aid, and we are forming that tube out of streamlines. So this sounds okay to me. Describes the path of a particle. No, that's going to be a path line for you. So that is also an important tool that we might use later. Okay, so now we have the last question, that is the incompressibility condition for the Navier-Stokes equation. Okay, so we all know that the answer to this is this, right? This is something we must have learned in elementary fluid mechanics classes. Now let's refresh why the answer is A, that is the del dot u is 0, or divergence of the velocity is 0. Why is that the answer? So let's have a look at the continuity equation for any fluid. I'm not going to be restricting myself to the incompressible fluid. For any out fluid, let's see what that looks like. Right. So I'm just going to be breaking down this derivative term. So I have over here u d rho by dx plus rho du by dx, and then I have v d dou by dou y, and rho dou v by dou y plus, where is I? Yeah. Okay. So these are all of my terms equal to 0. So this is just my continuity equation for mass continuity. This must necessarily be true for any flow. Unless, and over here we have a 0 over here in this case, because fluid cannot be spontaneously generated unless we have a source of some kind. But over here, for any odd flow going through a pipe or any place actually, should have a source term equal to 0 unless there is some generation terms, but we'll not talk about that much. And yeah, so this is the whole expansion of all of the terms that I have in my mass and continuity equation. So let's group them. So I see over here that these are my velocity components, and these are the components, and these are the components of the gradient of my density. So I'm able to instantly write down. So here I'm going to skip the write the flow velocity as a capital V, or should I stick to U? I should stick to U because that's what the question has asked me to do. So then my flow velocity, that is U, where U is equal to U I cap plus V j cap plus W k cap. Okay, so bear with me over here. This U represents the entire velocity of the flow. So then u dot gradient of rho. Okay, plus I have over here, let's see what the other three terms look like. I have rho is multiplied with this term, right? So for incompressibility, what we need is that the gradient of density in time as well as space. So this is the spatial gradient, while this is the temporal gradient, that is the gradient in time. So these both should be zero. Like the sum of them should also be zero for incompressibility to be a condition, because basically we don't want any change in density. So then if these both are zero, then what else is zero for this equation to be 2? Then my term over here should also be zero. Now in this term, density cannot be zero. It is physically not possible for it to be, for density itself to be zero. Therefore, what we must have is this term, that is del dot u, must necessarily be zero. Therefore, for incompressibility, okay, okay. So now we are done with the assignment for week 0. If you have any questions regarding this, you can mail me on my email ID. So let's write my email ID also over here: ae19752 at the rate of smail.iitm.ac.in. Okay, so you can mail me over here. Hopefully, this should be fairly easy, because this is just an introductory kind of an assignment for us to get comfortable with the topics that we'll be discussing in this course. So that concludes the class for today. Thank you, and see you next time.